and I'm gonna. Okay, so I'm Benedikt. I'm gonna do this presentation about agent-based graph neural networks, and it's part of the distributed systems laboratory. And I was supervised by Carlis in all this work. Yeah. So we're gonna look at the problem of graph classification and more generally like graph neural networks. And so the idea is you have an input graph and you pass it through the neural network and you output the graph label, so what class it's part of it. And currently, most graph neural networks will follow a message passing paradigm where each node has a certain embedding and it will send its embedding to its neighbors and everybody will update embeddings and multiple hops will be done. This has a few problems. One of the big ones is that it will be hard to scale this to, let's say, graph with millions of nodes and millions of edges. And a second problem is if, for example, we have very critical information between two nodes that need to communicate, which are 10 hops away, and we only do 6 or 7 hops, then this information will never reach and we will not do the correct classification. So long distance relationships are hard to capture. And we introduce a new approach to graph neural networks based on agents, and it's somewhat inspired from sublinear algorithms on graphs. And the way it works, so the idea behind it is that we take an agent and it walks around the graph, it learns about the graph, and then it outputs a prediction about the graph. And so here we have an example with one graph, and the idea is that our agent will just walk around and just explore the graph, and let's walk him around, like he goes from one neighbor to the other and learns about the graph and its structure and all the embeddings. And then at the end, it reaches the final node he wants to reach, and he can output the class of the graph. And in case like you did notice, this cat, and so we will call this AgentNet, and we're going to explore a bit how it works exactly. And globally, our agent works by having agent positions where our current agents are on which node. We have each agent has an embedding, and each node also has an embedding. And we pass them through what we call an agent hop layer, which I will talk a bit more about it later. But the main idea of this layer is that we update all the embeddings, and the agent also does one hop. It goes to one of the neighbors. Then we pass all the embeddings through a layer normalization, and we do this multiple times. And now we can do, for example, easily 32 hops or 64 hops if we reduce the number of agents. And the way we do the readout is not complicated. When at each moment there's an agent, at each hop we have the agent embedding, and we compute the max and mean out of it. And we also take of the node embeddings, we take the mean of it at the end, at the final layer. We pretty much concatenate all this and process from NLP, and we get the class prediction, and this gives us the final label. And so now we want to dig a bit deeper into what exactly happens in the agent hop layer, because it's the critical part. What are all the updates we do? And so here we want to, in an AgentNet, we want to rely on an attention mechanism. We want to use this such that the agent gives a query vector out of the agent embedding, and each of the neighboring nodes gives a key. And when we multiply the two, we get the attention scores, which gives us the probability of sampling that neighbor. And so the way it works is, for the query, we use the agent embedding and the node embedding of the currently visited node. So in this case, the orange node. And for the key, we just use the node embedding. And of course, we always only consider the adjacent nodes, so the neighboring nodes. And we pass these probabilities through a Gumbel softmax, which allows us to sample one of the nodes and also allow for differentiation to work properly. And this gives us a new agent position. So our agent just did one hop. Then what we also have to do in this layer is update all the embeddings. We have to update the agent embeddings and the node embeddings. So what actually happens here, the way to simplify it is we take the agent embeddings, the node features, and the node embeddings to predict the new node embeddings. So the delta, so because we actually use a residual connection, we compute the new node embedding. And then we update the agent embedding based on the new node embedding and on the agent embedding and the node features. Why do we do this in this order? Well, the reason behind this is that when multiple agents are on the same node, which might happen, we actually take the average of the updates to update the node embedding. And so we do the agent embedding after node embedding because multiple agents update the same node. We want to be sure that the agents are aware that another node is present and also did an update, such that the agent can take into account this information. And this is also a critical part, which I will talk about a bit later. This is something a bit important, how we do these updates. And we want to compare, so we want to evaluate our agent compared to some baseline which we create. And the first baseline which we have are called the random path GNN. So it's the same idea as the agent net, but here instead of sampling using an attention-based mechanism, we will just sample randomly. Any of the adjacent nodes will just be sampled randomly for all the agents. And also we will do, instead of doing the agent embedding update after the node embedding update, they will be done in parallel. So they cannot know if multiple agents are in the same position. Another baseline which we have is the global attention GNN, and this works a bit differently. The agent no longer gives a query, but we pass the node embeddings through an MLP to give the score, to give the attention score directly. And this means that for all the agents, they will all have the same scores. This can also cause a bit of problems that maybe they all end up on the same nodes. So this is not necessarily the best, but it's one of the baselines. And we will also compare our scores against the GIN, which is the more classical approach to GNNs, which also uses message passing. So we have evaluated on three data sets, but let's first consider the first one. So on the top row, you see all the final scores from MUTAC, and always on the y-axis you have the number of agents, and on the x-axis you have the number of hops, which increases. And on MUTAC, it's very interesting because immediately, even with almost no hops and almost no agents, we immediately get super good scores, 0.86, which we believe comes from the fact that it directly does the prediction based on the final node embeddings, which do not really, which means that he's directly taking the features, he directly learns from the features, which means that he doesn't really care about the agents in any way. And another interesting part of this is that we see that with a lot of hops and a lot of agents, the random path seems to struggle. So the gradients are probably not as good, but with global attention and AgentNet, they manage to counter this effect. And GIN reaches a score of 0.9, which is slightly better than the 0.87, which we reach with our agents. And also notice that in AgentNet, if we take the last column, we see that the lower, so we have a lot of hops, the lower the number of agents, it tends to be better. So this is something we will see again on this new 4 cycles data set. So here in this data set, what we try to do is we have a graph of 60 nodes, and we try to see if the graph contains a cycle of length 4. And we evaluate our, again, our 4 approaches, the random path, the global attention, and AgentNet. GIN does not solve this task, it was reaching only 0.5, and with a random feature for each node, it reaches 0.77. Random path is quite close with 0.76. Global attention already manages to meet with a best score of 0.94. Each time you see that it does require a lot of hops. And finally, AgentNet reaches 1, which means that it manages to solve this task perfectly, which is good. But notice again here we have the same pattern. When we increase the number of agents, we don't get as good scores. We believe that this is because simultaneous agents on the same nodes damages the performance because they try to do different changes on the node embeddings, and this is not good for this task and more generally for the network. We also evaluated on the. Oh, what's going on? Okay. Sorry. Okay, I'm sorry. I don't know why this is suddenly pixelized. Oh, sorry. So, Okay, I'm sorry. This is sadly pixelated. I cannot show it properly, but yeah. So here we tried it on RGB Molheave, and the most interesting plot is actually the right one. So I will try to explain it. It's very, very pixelated. I'm really sorry. And it just shows the testing, the area under the curve of the RC plot, and actually global attention is slightly above AgentNet, which is the second one, and then the bottom one is the random path agent. And so it does show that AgentNet is not necessarily the best. The global attention seems to do a bit better here, but in this data set, be a bit careful. The numbers are not, we don't think that the numbers are really optimal, that the configurations of the agent is optimal, because we only reach a score of 0.67, which is quite a bit lower than Jin, which reaches 0.756. And actually, this morning, I even got the results for another configuration where we could reach 0.72. And another thing to consider is that this data set contains 8 features, which we do not support right now. So the AgentNet is a bit as a disadvantage here compared to the other models. So we would like to show you something else, which we created a small visualization tool to see how the agents navigate the graph. And here we take the 4 cycles data set as an example. And you have the agent, which is labeled as 1, and the agent 0, which is labeled as 0. And here's the case where the agent perfectly classifies it. And we want to see a bit the exploration strategy that the agent adopts. And in this case, we see there's a graph of length 4. And we're going to run and see what it's going to output, how it's going to navigate the graph. And so it will do 32 hops, as we saw before. And notice that 0 just walks around in its graph. It does seem to always follow the same path. And agent 1 just stays on one node, goes forward, stays on one node, goes forward. It does this until it will actually do a full circle. Now it will reach the full circle. Now it has done a full circle, and it will go back. I don't really know why it goes back, but it seemed to have counted the number of nodes on that chain. And we're going to see how this works also in our next example. On this one, where we don't have a 4 cycle, and how our agents are going to navigate. Here in this case, the agents actually appeared on the same node. So this is also quite an interesting case. And they go forward, stop, go forward, stop, and they keep doing this all the time. So this seems to be their exploitation strategy. Sometimes it also happened in the previous models. They just go once back and then they continue their path forward. I think this could connect off the random feature, but we're not sure on that. But so most importantly here is that it does seem to have a structured exploration strategy. It does seem to count the number of nodes along the chain, more or less. And so it does seem to have a certain structure behind it, which is quite important. So it does seem to be able to learn something quite useful. And so in this work, we proposed a new way to graph neural networks, which is not based on message passing and instead based on agents. We managed to get good performance on 4 cycles and on NewTek decent performance, but there's still plenty of work left to do, especially to get really competitive results. For that, for sure, we're going to need support for edge features, especially for the Molheave dataset and for other datasets, which tend to often have edge features. But there's also some other work about the agent itself. As I said, there seem to be a problem when multiple agents are on the same node. There seem to be conflicting nodes, conflicting updates on the embeddings. And we actually tried, I didn't present this in videos, but we actually tried different versions of the model where we had different ways of doing these updates. And it's quite unclear which approach to doing these updates is good, and how these should be properly handled. So there's still work to do on this area, especially since it's quite a critical part. So thank you guys for coming, and I would like to thank Carolis for supervising me. It was a really interesting project, and there's still some things left to do. So and if you have any other questions, please don't hesitate.
Right, thanks. Good questions. Yeah, let's start with questions.
Hi, thanks for the talk. So I haven't had time to really think about it. A bit tired, but does the does it definitely not fit into the message passing framework, or how is it? What makes it not fit into the message passing framework? What makes it different?
Well, so let me just go to the first slide. A big difference is that, so there's one similarity is that we still have node embeddings. This is something we should get rid of at some point, ideally. This is true. The difference here is that the agent should have their local embedding and walk around and do an update and update the corresponding node embedding. So here the node embedding will do an update based on the path of the agent and not based on all the surrounding nodes. And already this means that we can learn on far longer chains because it's only based on one path and not all the node embeddings. And this is the main difference between the two approaches. And this means also that we can have, we don't necessarily have as many agents as the number of nodes. And it means that even sometimes some nodes will never be visited and some messages will never be passed like it would happen in a normal message passing framework.
Mm-hmm. Yeah.
So I'm still struggling with this idea that less agents are better. So does it mean that you trained for exactly the same amount of work, so that if you have less agents, they do more work than if you have more agents, or what is the reason? You said they're on the same node, but this is something I found surprising. But
yes, exactly. I think another way to see it is exactly in that way with the way of work is that each agent has more work, so it can do more hops. But then the trade-off is that we cannot have as many agents, so we have to reduce the number of agents.
Mm.
And so this is a bit of a trade-off. So we try to investigate if exactly having a lot of hops cannot result also in good performance instead of having like a lot of agents, like it would technically be the approach in more message passing frameworks.
So the difference is the number of hops versus the number of agents, so to speak, and not it could be other things, right? But okay, so that's the difference. Okay.
Exactly.
Yeah.
And you could draw if you would have like a lot of agents, it would in a way approximate a message passing framework. Not be perfect, but it would approximate. Mm-hmm. So in a way that would probably happen.
Yeah. Hi, I also had a question. So if I got this correctly, you kind of construct your computation graph randomly as your agent moves around, to some extent randomly, right?
So for AgentNet, actually during evaluation, not really, because when we will give the score, the attention score, we will always choose the neighbor with the maximum value, and then we will always jump to it. So it's not really random. But during training, it will be random. We will evaluate any of the neighbors randomly.
Yeah. And you use kind of for back propagation, then you use kind of a reparameterization trick with the GAN softmax? Or how do you back propagate through this random choice?
Yeah, yes, exactly. I think the idea, so we use exactly this Gumbel softmax, which I think, it can be considered as a reparameterization trick. I'm not exactly sure. But yes, the point is that we sample out of the softmax. This allows for the differentiation to work. Sadly, I cannot give you the exact details of how this Gumbel softmax works. But yeah, I think it can be classified as a reparameterization trick. Not sure. Sorry.
Maybe I have another question. So you're maybe the first one who tried something like this. I'm not sure what is the related work here, and it looks somewhat promising, right? It's not so much worse, and sometimes even better than other state-of-the-art functions. Is there something what is your tip for us, so to speak? Is there something we should do differently when we continue doing this, or is there? Since you're now an expert, the world-leading expert topic.
It's easy when it's a new topic. I think currently the actual agent has become maybe a bit too complex. Too many updates. This is what I started to believe a bit, that the agent has become a bit too complex. Especially we use a lot of skip connections because all these graphs don't really show all the skip connections goes along. And so I think I would actually like to try to simplify it a bit. And another important part is, as I said, to add support for edge features, because most graph, especially in OGBG, most graph classification datasets require edge features to perform well. So this is also another part. And yes, one critical part was also how do we do the updates when multiple agents are on the nodes? This is something which needs to be explored further than I did. Because we tried multiple approaches also with attention mechanisms and different models, but I didn't really manage to really get the best, to really get a really good version. It would be perfect to have something which could perform really well with a lot of hops and a lot of agents on the 4 cycles. I think this would already mean something that it would already mean that the aggregation function is good. Yeah.
Mm-hmm.
Hey, I have maybe a different question. Like you said at some point that you would like to move away completely from the node embeddings on their own. And my question is just now, like, would you see any benefit in actually doing some parts like first step, like classical message passing to get some node embedding and then use your agents? Would you see why that could work or not work?
Okay, so if I understand well, you still want to keep the node embeddings. But the idea of getting rid of the node embeddings is for scalability is that, I mean, if you have, the main idea is if you have like millions of nodes, it's harder to keep track of all the node embeddings and to do all the updates. So
I see. Okay.
This would be quite a challenge.
That makes sense.
But it's true, we would still have to load node features and somewhat embed them. So of course, we cannot completely get rid of them.
Because, or my idea behind that was that, like, if your agent maybe doesn't visit all the nodes, if you have some message passing first with like just a few hops, then maybe even if your agent misses an important node, it could still get the information in some embedding.
Yeah, it's true. Maybe it could help with like a local subgraph embedding. This could help, but in a way, it does kind of could help. But then I'm not sure if it would make much sense in the end.
Yes. No, I see your point with the
it's true that
scalability.
But it's true that, and actually we wanted also to maybe explore this a bit, that when the agent is on a node, it not only learns from the current nodes, but also from the neighboring nodes. Like it takes the embeddings of the neighboring nodes to learn, and such that it visits a local subgraph instead of just visiting one node. This could also help, and it would be a bit similar to what you propose.
Yeah, that's basically the same idea.
Exactly, but it would also not necessarily need the edge embedding, the node embeddings in that case.
Yes, fair. Yeah. Okay, thank you.
Just as a comment here, where I see where this could definitely already give kind of a boost is that you could simply use a GNN in pre-processing, as Benjamin said, to get the edge embeddings in there as well, right?
Yeah, that's true.
You can use the GNN that uses edge embeddings to get the edge embeddings, the information from the edge embeddings into the node embeddings, and then use your agent on the node embeddings. True.
But I think, but then it comes back to the same point. If we should use some GNNs before we apply our model. But I think we should also explore. I think there should also be some exploration on adding these edge embeddings, because I don't think it's that hard. Like I actually had some versions running which supported edge embeddings, where we simply just, I mean, when an agent takes an edge, we just add to the agent such that it doesn't update. We just add the edge embedding to it. I don't think it's that hard to get it added to the model itself than having to add it to the gen. But both can definitely be a way.
Yeah, I mean, one thing that I could see here is also when you create the kind of attention weights for where the agent wants to move. In these, instead of just using the agent and the target node, you can obviously also take the edge that leads there as an additional input.
Exactly. The extension to edge embedding is somewhat natural. I mean, but it's true. I also thought about this, but in the actual code, it's actually to add this is actually a bit harder than you would expect. But.
Very good. So no more questions, it seems. So thanks again for your presentation.